Hello, welcome to our lecture on the quantum model of the atom. We're going to start off by talking about Bohr's model again, and unfortunately, it has some problems. As it turns out, the model doesn't work for any elements that have more than one electron. It only worked for the hydrogen atom. It could not predict the emission spectra of any other elements, and every other element's emission spectra didn't make sense in the same rules that Bohr provided. It's sort of assumed that electrons were in a fixed orbit around the nucleus, like a 2D shape. There's no 3D to it. He just thought they were orbiting around like this. And that turned out not to be the case. To understand the quantum model, we first have to talk about Heisenberg's uncertainty principle. Basically, this scientist Heisenberg uh, wrote this uncertainty principle as for what we were observing in terms of how particles work. And basically, he found that it is impossible to determine accurately both the momentum and the position of a particle simultaneously. It just couldn't happen. If you knew how fast a particle was going, the momentum, you had no idea where it was. And if you knew exactly where a particle was, it had no momentum. So the more we know about it, the less we know how fast it's moving, which is exactly what I said. This makes it impossible to exactly pinpoint the location or trajectory of an electron because if we know the position, we don't know it's not moving, and so that's not helpful for us in terms of understanding actually how electrons work because electrons are basically always moving. But we can calculate the probability of an electron being in a specific region of space at a given time. If you can think about it in terms of an example, if you were asked, like at any given point throughout the school day, where Dr. Johnson was, you probably wouldn't know exactly where she is because you're not observing her. If you could see her in the classroom in front of you, she wouldn't be moving anywhere because you know exactly where she was. If not, you might have some idea of where she is, like she might be in the science office or she might be somewhere in the school. And that's the same thing. We can't know exactly where an electron is, but we can give a region of space. Like, for example, Dr. Johnson will be somewhere in the school during the school day as our and a probability for how likely that is to be true. So we can come up with the likely place an electron would be in a given region of space instead of just a specific point that it always is, if that makes sense. So, in 1926, Erwin Schrödinger, which you may have heard before, related to cats, developed the basis for our quantum model of an atom, taking Heisenberg's uncertainty principle and working it into atoms. Here's a picture of him. Great guy. So, this is what he said. Electrons have definite energy levels, which is the same that Bohr said. So we still have our quantum, our primary quantum numbers of n equals 1, n equals 2, and so on and so forth. Electrons themselves are both particles and waves. Electrons have no prescribed trajectory. Instead, he created a mathematical formula to calculate the probability an electron will be in a specific location depending on what energy level it's at. These regions of spaces that he calculated, that an electron has a high probability of being at, are called orbitals. This is his evil equation that he used to create it all. You don't have to know this. I just wanted to show it to you because I had to do stuff with this equation in my quantum mechanics class. And it's an evil equation. It's an evil equation. You got derivatives. You got partial derivatives. You got friggin' Poseidon's trident. What's that doing there? I don't know. He's a crazy guy. He did a lot of math. He was a mathematician more so than a chemist. But through all that math, he found out these specific orbitals at different energy levels. And orbitals are the region of space that an electron is likely to be in at different energy levels. So, here is it sort of physically. This would be you go through all the calculations of a specific orbital. These are all of the locations that an electron would could be at a specific orbital, most likely. That is very jumbled up and messy. So usually we simplify it to just drawing a specific shape around the most likely area. So we just draw a circle around it, and that is the orbital shape. Each of these specific orbitals at the energy levels can hold two electrons, just two. So at any given point, those two electrons could be here and here, or so on and so forth. Any of these dots could be any of the two electrons that could be held at this orbital. So when n equals 1, there is one orbital that could be there, and it's this ball one that I showed you before. Now, it's important to remember, because even looking back in here, it's 2D, but these are 3D shapes. Orbitals are 3D. This is a actual like sphere, like a ball. It has a X, Y, and Z dimension, which you have probably seen before if you're taking physics. But if you're not taking physics, this is how we would draw a 3D plane. It's the first orbital. We call orbitals this ball. We would call this the S orbital. Then at n equals 2, we would have a S orbital, but we also have these three p orbitals. These three p orbitals are shaped sort of like they're described as like the dumbbell shapes, where you have them against like along one of the axes. So for example, these p orbitals are along this first one's the px, and it's along the x-axis. This one is along the z-axis, and we would call it pz, and this one is along the y-axis, and we would call it py. So this is our 2s orbital because we're at n equals 2. And then we have the 2px orbital, the 2pz orbital, and the 2py orbital. Now, you might be thinking, why did we only have one in the first one, but we have four orbitals at the second energy level? And it's that same formula we saw before. The number of electrons is equal to 2n squared. So we have 2, that's equal to 8. And we know each orbital can hold two electrons. So at the second energy level, there's two electrons in the 2s orbital, two electrons somewhere in the 2px orbital, and so on and so forth. When we get to n equals 3, we have the 3s orbital, our 3p's orbital, and then our 3d's orbital. These, I don't even know, because some of the shapes are really weird, but these are the different shapes along the different y-axes. It's important to recognize what the d orbitals, all the different orbitals look like. So keep that in mind, but you don't have to like be able to draw them from memory. More so if I were to like show you an orbital, you'd be like, yeah, that's a d orbital. And because we're the third energy level, you'd put a 3 in front of it. So this would be a 3s, be 3px, and so on. For the d's, you can write it like they have here, where it would be 3d minus 2, 3d minus 1, and so on and so forth. And obviously we have more orbitals because when n equals 3, our number of electrons is 18. So each of these has 2, so there should be 9 orbitals at this level. When n equals 4, we get to f orbitals, which you can see here. F orbitals are crazy. Crazy shapes all over the place. Mathematically, they were determined, and that's what they look like. It's the same thing. The max number of electrons is 32. 32, excuse me. So we have 16 different orbitals. Remember, Each orbital holds two electrons, and they can be anywhere in the shapes that we see here. So like even when we have 4f 3, both electrons could be like right here in the section. These are just the most likely areas the electrons would be at a specific orbital at a specific energy level. Thank you so much for listening. I know this one is pretty heavy topic. Feel free to go over it again, or if you have any questions, come and ask me in person as well. Thank you so much for listening.